In this video, I want to show you an example of an improper solution that you can get sometimes in confirmatory factor analysis or structural equation modeling, and I want to show you what it looks like in the Mplus program when you get such an improper solution, what it means in this case, what the causes are, what the reasons are, and also I want to discuss a little bit what other reasons can be for seeing those types of improper solutions. So here I'm going to analyze a very small correlation matrix that is taken from an example discussed in the book by Johnson and Wichern, 1998, Applied Multivariate Statistical Analysis. In this book, they presented an example of a correlation matrix that leads to an improper solution when you analyze this correlation matrix with a single factor model. So specifically in this example there are three observed variables, y1, y2 and y3, or we could say indicators, and the assumption here in the model is that those are indicators of a single factor f. So you can see that the model here in Mplus is specified as f by y1 through y3, which means Mplus will estimate a single factor congeneric measurement model where all these variables load onto this factor and they have different loadings and they have uncorrelated error variables. Now let's take a look at what happens when we estimate this model here in Mplus for these data. Note that since we're reading a correlation matrix here, which is summary data, we have to tell Mplus that the type is core, so meaning we're not analyzing raw data, we're not analyzing a covariance matrix. In this case, we're analyzing a correlation matrix. There are some issues with analyzing correlation matrices with confirmatory factor analysis and SEM that I don't want to get into here in this presentation. That's a topic for a separate video. Now for this example it doesn't really matter, but keep in mind that it's not always a good idea to analyze a correlation matrix because a correlation matrix doesn't have the same amount of information as a covariance matrix because all the variables are standardized, and so we're losing the information about the variances when we're analyzing a correlation matrix as opposed to a covariance matrix. So in short, it is usually better to analyze a covariance matrix. Now again, for this example it doesn't really matter because we would see the same thing here if we were to estimate the corresponding covariance matrix for these data. Also in Mplus what we need is the sample size subcommand n observations, or n-ops, gives Mplus the sample size. In this case we're assuming the sample size is 1,000 cases because from summary data we can't directly infer the sample size because all that it is a correlation matrix or a covariance matrix, and so there's no way to find out what the sample size is for Mplus just simply based on that summary data set. So that's just as an aside here, we're analyzing summary data, and so we need those two additional commands here in the data command to tell Mplus what's going on with this summary data file. Now let's take a look at the output for this one factor model for this example. And so first thing we see, input reading terminated normally, so the model works, so to say, or the syntax doesn't have any problems. We have 1,000 cases here, and when we scroll down we get the message the model estimation terminated normally. So Mplus was able to generate parameter estimates and fit statistics. However, there's a warning message as well that says that the residual covariance matrix theta is not positive definite, and that this could indicate a negative variance or residual variance estimate for an observed variable, or a correlation greater than or equal to 1 between two observed variables, or some sort of linear dependency among more than two observed variables. Mplus also tells us that we should look at the results section, so the model parameter estimates, for more information, and that the problem involves the variable y1. And so that's helpful because then we can already assume that there must be some problem with the indicator y1. Now typically when you get this message in Mplus, it almost always means you have a negative residual variance estimate. So the error variance for an indicator or for more than one indicator is estimated to be 0 or negative, and that is something that is, especially when it's negative, is something that is not meaningful because variances by definition cannot be negative, and so a negative variance estimate then is strange, it's weird. It can happen in structural equation models and confirmatory factor analysis analysis for a number of reasons, but it's usually a sign that something is wrong with your model, with your data, and there are different reasons for that I will go into in a little bit. But let's take a look at it first. Let's take a look at first what else we get. You can see you still get model fit information here. In this case, the chi-square test of model fit is 0 with 0 degrees of freedom. Now, this doesn't have anything to do with the improper solution, but that has something to do with the fact that a one-factor model with different loadings between indicators is always saturated when you have just 3 indicators. So the model then always fits perfectly, regardless of whether you have an improper solution or not. The model is saturated, it has no degrees of freedom. All the information in the data is used to estimate the model parameters, and so there's nothing here to test, so to say. In this case, this would be different if you had 4 indicators or more indicators, and then you could still get an improper solution, and you could still get a chi-square test that is not 0 with non-zero degrees of freedom as well. So this means the model fits, so to say, trivially perfectly. However, it's not okay. The solution is not proper. Let's take a look at where we can see that. So we should carefully check our model results section with the parameter estimates. And you can see from the unstandardized parameter estimates here that there is a negative residual variance estimate for Y1. So exactly as Mplus indicated that there was a problem with Y1, that's exactly the issue here, is that this residual variance estimate is negative, and that doesn't make any sense. You can see the standard error for this variance is pretty small, so that is a significant negative estimate in a sense, and that's weird because it couldn't really happen that some indicator has an explained variance that is above 1. So that would correspond to an R² value for that variable above 1. So more than 100% of the variance in this indicator is then explained by the factor f, and that doesn't make any sense. Another reason, or another way you can see this problem is by looking at the standardized solution. When you have a loading above 1 in a simple structure model where each indicator loads only onto one factor and no other factor, then a standardized loading couldn't be above or shouldn't be above 1, because again that would correspond to an explained variance R² of greater than 1, and so that doesn't make any sense. So that's also a sign here that's directly related to this negative error variance estimate here. Now, what else can you see? When you go to the R² at the end, you can see it's undefined, because that's the standardized loading squared in this model, and so that doesn't make any sense to have an R² greater than 1, and then Mplus doesn't give it, and it says the R² here is not defined. You are explaining more than 100% of the variance in this indicator, and this doesn't make any sense. Now, let's talk a little bit about why this can happen. So in general, improper solutions, negative residual variances often happen when a model is misspecified. And I'll talk about this a little bit later to how this, I think this explains this issue in this case. In my opinion, this model is just simply misspecified here, despite the fact that it's saturated and fits perfectly. So to say, there's still a dimension here of misspecification. Now, this one reason, that's often a reason, is that there's a model misspecification, meaning either the model is too restrictive or the model is overly parameterized. You have too many factors in the model. You have indicators maybe that are not homogeneous, that are not measuring just one factor, and you're squeezing them onto a single factor, and that and they're so different in their correlation structure that it doesn't make sense for them to be measures of a single construct or single factor. Another reason can be when you have a sample size that's too small. There can be a lot of sampling error, and then the sampling error can cause a covariance or correlation matrix to have values that then are not in line with this model, so to say, or that lead to this improper solution just simply due to sampling error. That's also a reason, but the most typical reason in my experience is model misspecification. So something about the model is not right. And that's also, in my opinion, the case here, because that, we can see that pretty well from looking at the correlation matrix that was provided in that book for this example. So here we have, under the sample statistics, the correlation matrix that I analyzed here. And you can see that the correlation between y1 and y2 is very strong, 0.9. So that would be in line with a single factor model for these two variables, meaning these two measures seem to be measuring the same factor because they're correlated 0.9, so that makes sense. Also, y1 and y3 are correlated 0.7, so that still probably makes sense to say y1 and y3 are measures of something similar because they're very highly correlated. But then you can see y2 and y3 are only correlated 0.4. When two measures are only correlated 0.4, does it make sense to assume that they are measures of the same construct, the same factor, like, for example, intelligence or personality or depression? Well, it's more questionable, right? Because 0.4 is not a very high correlation. And so then this means if you square 0.4, you don't have a lot of explained variance. You only have 16% explained variance. So the correlation squared would be the variance that they shared, and that would be 0.16 in that case. And so 16% common variance is not a lot. So then does it make sense to assume that y2 and y3 measure the same factor? I wouldn't think so. So I think that then probably y3 might be measuring something different or some additional factor. So maybe there's a method effect that causes y3 to measure some additional factor or some method factor, or indicator-specific factor, and then that model with a single unidimensional factor doesn't really make sense. If all those indicators were randomly sampled from the population of indicators for that construct, they should have about the same correlation, meaning there should be greater homogeneity in these correlations. They should maybe vary, let's say, roughly between 0.7 and 0.9. They could also be lower. They could vary between, let's say, 0.6 and 0.8 or something like that. But they shouldn't vary that much. So there shouldn't be that spread between 0.4 and 0.9 for a unidimensional construct. So this means that we're either omitting a significant additional factor for y3 or another indicator, or that there's a method effect, or that simply that one indicator doesn't measure the same construct, but instead that it measures something different. And so therefore my opinion here is that my point of view from a psychometric perspective is that this model is inadequate because it assumes a unidimensional structure, and a unidimensional structure is not in line with a correlation spread that is so big, because then we're confounding a lot of measurement error with systematic factors that are not in the model. And so let's take a look at the output one more time. There's also another way you can see this, or another place. You can see that the standardized loadings are very different, in addition to the first loading being improper. But the other ones are fairly low, especially the third one is only 0.558, and so that corresponds then to an R squared of 0.311. So 0.558 squared is 0.311. That's the R squared for that variable. In the sense of classical test theory, in the sense of the congeneric measurement model of classical test theory, we would interpret that R squared, or squared standardized loading, of 0.311 as a reliability estimate. So that would mean that this variable only has a reliability of 0.311. Only 31.1% of the variance in this indicator would be true score variance, and almost 70% of the variance in that indicator would be error variance. And that's not plausible for most measures that we're using. When we're using, at least in psychology and other social sciences, when we're using test scores, then typically they're more reliable than that. So this means the model underestimates the reliability of this indicator, very likely. And so that means there are other factors, other systematic sources of variance that are not in the model. And so from that perspective, the model is underspecified or misspecified because it doesn't take that into account, and it provides an implausible estimate of R squared, or in the sense of reliability. And so then from the perspective of classical test theory, from the perspective of the congeneric measurement model, we would say, well, is it really plausible that the indicators have such different reliabilities? Should they not be more reliable? And also, obviously, a reliability above 1 here for y1 is not okay, it's not plausible and possible. And even a reliability of exactly 1.0 is completely unlikely to happen, because we never have 100% true score variance in the social sciences, and there's always some measurement error. So from that perspective, this model is inadequate. So what should you do then? I think in this case, if you have something like that, which happens actually quite frequently in practice, that you find a measurement model with an improper solution where you have a similar, very inhomogeneous correlation or covariance pattern, what I would recommend is then getting rid of the indicator that is not so highly correlated with the others. If you don't have another way of accounting for method effects or something like that that is obvious. So in this case, I would say maybe just retain y1 and y2, because they seem to be homogeneous measures of the same construct. They are correlated 0.9. So that makes it plausible that these are measures of the same underlying factor, the same underlying true score. It's not plausible that the indicator y3 here is also measuring the exact same construct. So I would probably get rid of that indicator if I didn't have some other option for modeling those additional factors that might be reflected in y3. And so that would be a solution in this case, to only pick those indicators that are highly homogeneous, for which it makes sense to assume that they measure a common true score factor, and get rid of other indicators. Okay, so another possibility would be to look for other indicators if you have maybe other variables of the same factor that you think are indicators, and see if those have a better pattern, so to say, where you get a better model without an improper solution, but that may not be available. And so in that situation, it might be best to just simply go with those indicators that seem to be the most homogeneous. I hope you liked this little video about an improper solution in Mplus and what to do. If you're interested in more tutorials like that, please subscribe to this channel. Also check out the description for more videos on advanced methods, and leave a comment in the comment section if you have other topics that you would like to see discussed, and I'll see you next time.